The last part of the ICS computational stack is the industrial protocol, and it is the way that the PLC communicates to other PLCs or to the centralized server or to some kind of another computational device. Before I proceed with the content about the protocol, I'd like to make a note of terminology. So historically, and you may see it in the readings and over the internet, the term master-slave has existed for decades. Nowadays, it's been a subject of controversy because its association with slavery, and many organizations are starting to replace it with alternative terms. For example, primary, secondary, primary replica, source replica. Depending on the application, there could be better ways to represent the idea of having a main device and a secondary device that are communicating, and who is actually initiating the communication and who is actually consuming the communication. So in July 9 of 2020, Modbus organization made a decision to replace the term master-slave with client-server. And this is what we'll do in the class as well. This is the last time I'll be mentioning that term. But I want to make sure that when you read, and if there are remnants of the term found on the internet or in some of the readings or books, you understand what this exactly means. So master-slave is being replaced with client-server, and I want you to be mindful of potential confusion. So client is the one that initiates the communication. Client is the main device, that the one you would call a master in the past. Here we call it client because, again, it initiates the communication to some device that is waiting for commands. Same way you connect to a web server, you are the client, you type google.com, you're asking Google to give you back something. It's the same idea. You're the client, Google's the server. Here, the client is the main PLC that is asking the secondary PLC, or the server in this case, to respond to the client. So in a way, the secondary PLC can be also seen as a consumer or as a follower device. So the term master is replaced by client, and the term slave is being replaced by server. Second note, just a quick reminder of the OSI model. For the ones who don't remember the networks match, very quickly, the OSI model abstracts the communication, network communication in 7 layers, starting from the high-level application, presentation, session, transport, network, data link, all the way down to the physical layer. So in a way, in each layer, you're adding a header, some kind of header overhead coming from the protocol. The application protocol is adding something, is being moved to the presentation, session, transport, network, and then the data link is being transferred to the physical layer that through a data transmission path, could be over Wi-Fi, over wireless, wired, Ethernet, and so on. It goes to the other side that follows the reverse process. So the physical layer receives and starts removing the headers one by one to receive the final piece of data that was the initial communication. Example of protocols, physical layers, as again the physical medium that the communication takes place. It could be wireless, or it could be some form of wire fiber or coax. Data link, Ethernet, PPP, Internet Network, IP, transport, TCP. So you have the TCP IP, TCP is the transport, IP is the network, the routing part, how you actually route device, and the transport is how you actually transport the information across the devices. Session layers, so these 3 layers sometimes have been merged in the TCP IP model. So in session layer, you have sockets or various APIs. Presentation can be SSL, SSH, FTP, and the application layer is what the user sees. And this distinction here is important. Understand the OSI is important because sometimes industrial protocols look like regular protocols with modified physical layer, modified data layer. That's why the refresher is here. And I mentioned the TCP IP model merges the 3 layers, application to session, to an application layer, and the data to physical layer is also merged to the link layer. But we're concerned about the OSI here because most protocols are not regular TCP IP protocols in the OT environments. Right. So with the notes aside, let's move on to seeing industrial protocols. So there are four different ways of communicating, roughly. The first one that we'll see is point-to-point serial, so you have device-to-device communication with nothing between. Then we'll go to bus protocols. How does one device talk to many devices, but through proprietary buses? And we'll also see the alternative of using a standardized Ethernet-based protocol to have bus communication. And the last one that's newer and it's increasing in prevalence is wireless, that either peer-to-peer or point-to-point communication. But let's start from the beginning and the point-to-point serial. So point-to-point is simple, means you have one device, a cable, another device, and that's it. You have a receive and transmit unit and some grounding that takes place. So in the example we saw in the from the NIST handbook, you have your communication modem to modem. That's it's serial communication. Even though it's over the air, you can think of these the physical layer of this connection that can be wireless. So this the modem modulates, and through some radio communication, it sends again bits to the other side. The other side receives the bits, demodulates them, and then sends the information to the RTU. So even though this is over the air, it's still serial communication in a way. You communicate point to point from this control server SCADA to the RTU. You receive information back. So this receive transmit can be either over wires or either some other form of communication medium, in this example, radio communication. And that's the simplest one. If you want to talk to more than one device, then this point-to-point is not enough. You have to have some kind of a bus protocol that allows you to talk to multiple devices at once. And the DASA protocols, one side can be proprietary, as we see on this slide. Proprietary means that for example, the field bus family present here is also standardized as the 61784-1. In this, the physical data layer is proprietary. So you have some connectors that are not your usual connectors that you were comfortable with, like USB or Ethernet, RJ45, RJ11. So they have their own unique proprietary connectors, and also the data link, the way this works, is also proprietary and unique to the vendor. It could be collaboration across vendors and sharing of protocols, but the field bus is a family of protocols that implies that the lowest two levels are proprietary. In Profibus is an example where you have, for example, this is a daisy chain from one PLC, beginning PLC, you connect to a second PLC that connects to a third one. So this client PLC is talking to the servers, and you have a bus communication. So before we had only point-to-point, but this field bus protocol allows you to have one-to-many communication through up to 127 devices in this example. So this field bus family replaces the serial. So serial only point-to-point, field bus one-to-many, but it allows many topologies that are interesting. Ring topology, all PLCs communicate in a ring. You may have a branch, you may have a star topology with a main client, or you have the daisy chain I presented in the example before. So field bus allows you to have interesting topologies that fit the application and the control system you're currently engineering. We'll see the Ethernet-based protocols. So you can see they're similar to the field bus or the previous ones we've seen, but the difference is that the lowest two layers is regular Ethernet. It's also called industrial Ethernet. That is our familiar Ethernet that has modified MAC layer, the media access control, to make sure that latency is low and deterministic. So that's also standardized under 61784-2. And Profinet is the version, so before we saw Profibus, that was the protocol we saw, but there's a Ethernet version of it that is called Profinet. So the application layer is similar, but what's changing is the data and physical layer, that you have your regular Ethernet. So you see here the Wago PLC that supports Profinet, as it says on the label on the front of the PLC. It has regular RJ45 connectors. Instead of proprietary, this is your standard Ethernet, and you use a standard Ethernet cable to connect to that. So you can understand this is good because you can connect PLCs from different vendors, because they all support a unified protocol. And also to be able to talk to many different PLCs, you can use standard Ethernet switches or gateways to be able to get access to, to scale up your network to any number. Because Profibus from before could support only up to 127 devices. Here, you can support as many as you want, given that the Ethernet protocol is in place. And also you can have a version of it that is also over TCP/IP. So you can have the application protocol over TCP/IP over Ethernet. So here, this is how our computers also work. And we have our regular computers, HTTP connection here, and over TCP/IP over Ethernet if we connect through wire to our router. So we're getting closer in the protocol side to also how our computers work. So to put the comparison in a table, you see that what's different between Profibus and Profinet is mainly the two layers, right? You have a data link physical that's proprietary here, and here's Ethernet based. And since you have Ethernet based here, you have to also ensure that your transport protocol, here the transport is very specific, so you don't have to worry about the routability or that the way you transport data, the application layer takes over everything. Here, since it's Ethernet, you need routing offered by IP, and you need the way to transport offered by TCP, or you can also use UDP. So the physical layer is different, speed is different. Profibus goes up to 12 megabits. Profinet has the Ethernet limits that can be either 1 gigabit or 100 megabits. It can address up to 126 devices and the main client, 127. Profinet, you can have any number of devices. And Telegram is your standard packet. In Profibus it's smaller, 244. In Profinet is a bit bigger, but with those speeds, you don't really worry about bigger standard packet sizes. So these are the differences between the two. And the last one is wireless. Everything we talked about implies that there is a wiring process, point-to-point or the bus protocols, but you can also have wireless communication. And in this slide, I show a water temperature sensor that's based on Zigbee as an example. And Zigbee is also a standardized protocol that at the physical and data link you have wireless, like a Bluetooth standard, and you have the application interface that Zigbee based. So here the temperature sensor, you don't have to connect it through a cable. Maybe it's far and you don't have access to it and you don't want to run cables around your industrial environment. It may be much easier to just have a wireless sensor to be getting data from the field. So the wireless is also gaining popularity in industrial environments. This slide shows some common protocols. Fieldbus, we saw Profibus, but there are a few more. There's Modbus, RTU, CAN Open DeviceNet. Ethernet has also versions of older Fieldbus protocols. For example, there's Modbus TCP in contrast to Modbus RTU. There's DNP over TCP, there's EtherCAT, Profinet, that's the Profibus version with the Ethernet lower layers, Ethernet over IP, BACnet, and we have wireless, can be Bluetooth, Zigbee, or any IEEE 802X protocol that's on the Wi-Fi side. In terms of popularity, we've seen an increase of the industrial Ethernet solutions. So you see in the slide, from 2014 to 2018, more and more industries are using industrial Ethernet because of its flexibility, because of its ability to connect to different vendors, because of standardized equipment. There has been an increase to industrial Ethernet and a corresponding decrease in the proprietary protocol side, on the Fieldbus side. So in 2018, this survey shows more vendors, more utilities using industrial Ethernet compared to Fieldbus. And we'll see also wireless slowly coming up, and was up to 6% in 2018. So similar to the transition, to conclude, similar to the transition to commercial off-the-shelf hardware like ARM x86 and standardized software like Windows and Linux, we also see move to more standardized protocols like Ethernet-based protocols for communication in industrial environments.